Yeah, cam's on everyone. Let's start off. The last thing that we did, we started with the wave equation. Otherwise, you need to keep your cams on. So we have seen that any equation has to satisfy three conditions to be a wave. Now we will not be studying all this exponential and all these kind of things. We'll be restricting our study to very specific waves. So in our portion we will be studying waves generated by sources oscillating in SHM. So that means all your wave equations, right, will be sine and cos function only henceforth. We will not see that exponential and we will not see these kind of wave functions anymore. And even in that, we'll restrict. So for transverse waves, we study waves on a string. This is what we have in our portion. Later on, we also have a chapter called EM waves. That is for electromagnetic. We will see that later on. It's a separate chapter. For longitudinal waves, we study sound waves. So there. So this is we will study only this part. So how will your equation start looking like? So your general equation will look like y is equal to a sine k x plus or minus vt plus or minus plus y. So this is how your general equation looks like. It looks like kx plus or minus vt plus some constant. We can write this even better. Y is equal to a sine. Actually, you can keep this k outside. X plus or minus vt plus y. So this can be written as sine kx plus or minus omega t plus y. There, this is our general equation. So in this, A is amplitude. We'll talk about each term there. K is 2 pi by lambda. This is an angular wave number. Omega is your angular frequency. So in this, what is A, what is omega, all this we did in SHM. That K and lambda are something new. We will talk about that. In this, what is V wave? Coefficient of time by coefficient of X, omega by K. And omega was 2 pi F. And K is 2 pi by lambda. From there, we get F lambda. This is what you studied in chemistry, if you remember. Speed of light is frequency into wavelength. It is actually derived from here. So V wave is F lambda. This phi is called phase angle. And your lambda is your wavelength. So these are all the terms. Let's discuss few of them. Some of them you already know. So in case you don't know what are these, you should put it down. But yeah. So our wave equations will look like this. If you can see here clearly, if I put x is equal to constant, this looks like a sine omega t plus phi. Isn't that an SHM equation? So we have a source which is oscillating in SHM and that wave is being propagated. So last time I did send you some videos. I hope you guys have gone through them. I know I sent a lot, but there is one video. Remember last time I was saying what you're seeing is actually particles moving, and when you see all of them together, it gives you a feeling it is a wave. That is this video. Let me show you that. So here we have pendulums here. all have slightly different length, maybe 1 centimeter different. We know the time period of a pendulum is how much? 2 pi root over L by G. So when you disturb them, all will oscillate in SHM, their own SHM, but they'll all have different time periods. So they'll be little out of sync. I posted this in the group last time. You should check it out. I'll send it again today. Now see what happens if you take all of them and disturb them. So this is what I was saying. So think of this, all these are particles. Every particle has nothing to do with the other guy. Everyone is oscillating with their own SHMs. But when you take all of them together, what you see is looks like a wave. Now see when you leave it, can you see how it is looking? Doesn't that look like a wave? Now it feels like as if something is moving, right? But in reality, is any pendulum going front and back? Every pendulum is oscillating in its own plane. Did you guys see this video? So I posted this in the group. It was there in the last class. So look at this thing. See? There. Look at this thing. It gives you a feeling of, as if a pulse is traveling forward. So you can think of like this. It's not exactly the same thing, but this gives you that thing. So there, it looks like, as if a wave is moving. And then it goes out of sync and all. But yeah, that's what I was trying to discuss last time. Anyways, so yeah. Now in this equation, right, in some books now, you will see a sine kx minus omega t. Some books you'll write omega t minus kx. Both are right. The only difference is the phase difference. So if someone writes a sine kx minus omega t, just look at this thing. If I put x is equal to 0 and time is equal to 0, so the graph, right, is looking like this. So at x is equal to 0, the particle is starting with y is equal to minus sine omega t, meaning it is starting like this. If someone writes y is equal to a sine omega t minus kx, if you put x is equal to 0, it is y is equal to a sine omega t. Yeah, that's the only difference. So basically it is out of phase by pi. So the wave is starting like this. So both are right. The only difference is both are out of phase by 180. So y is equal to minus a sine omega t. So it is just the phase angle. So because I'll be using kx minus omega t. In some books you will see omega t minus kx and you'll think, oh, this is something new. No, it is the same thing. Just the phase is different. Clear with this stuff? Now let's talk about few terms here. Now if you look at the equation a sine kx plus or minus omega t, a is understood. A is the amplitude, maximum distance from the mean position. Now when you talk about that kx and all that stuff, so phase difference between 2 points, this is important. So when a wave is going, now in that SHM, the video just I showed you, if you see, every pendulum is having its own SHM, but all are not at the mean position at the same time. When you're at the mean, the other guy is somewhere else. When one particle is at extreme, the other particle is somewhere else. So every particle will have its own phase angles. They're moving differently, right? So if you take a yx graph and let's say this is a wave, remember a yx graph is a photograph. Yt graph is the position of a particle for one particle. So you have to be really careful whether it is a yx or yt graph. Most people go for there. Now see what is happening. If you choose a particle here, A, this particle A is always going up and down, A, right? And for A, this is the mean position. If you choose another particle B here, B is also going up and down. B is at the mean position. This is the mean position there. So at this point, maybe A is going upward, maybe at this point, B is going somewhere else. And let's say A and B ka beech ka distance is delta x. So now when you write the y coordinate for point A, look at the equation. So y coordinate of point A, what is the equation? A sine kx minus omega t. If you write for B, this would be A sine k, x has become x plus delta x. minus omega t. So this will be a sine kx minus omega t plus k delta x. So this extra term k delta x is your extra phase difference. So because both the particles are at a different position, they are going out of phase. And that is given by k delta x. So whenever a wave is going and they ask you what is the phase difference between 2 points, I'll give an example with some numbers what it means. So these are two pendulums oscillating in two different SHMs. They are out of phase by k delta x. And k is given as 2 pi by lambda delta x. A very useful thing. We want to use this in wave optics also. So this is the phase difference between A and B. And what is wavelength? So wavelength is the distance between 2 points in phase. Let's see what this phase actually tries to tell you. Lambda is 2 pi by k, yeah. Or k is 2 pi by lambda, same thing. See, this is what I was trying to say. I'll give an example, say. So we have a wave. So consider we have a point A here. And let's say A is going up at this instant. And let's say this distance is root 3a by 2. Let's say we have a point B here. And let's say B is coming down and this height is A by 2. Now, remember this, A always goes up and down, A doesn't care about B. B is also always going up and down, B doesn't care about B. Okay? So if you just look at this motion of A, so for point A, this is the mean position. A is somewhere here, going up at a distance of root 3a by 2. Anyone remember what is the phase angle then? If you are away from the mean position and you're going to the extreme, and if you're at root 3a by 2, then the phase angle of A is how much? 60 degrees? Is that fine? I hope you guys remember this. You should remember that sine theta root 3 by 2 is 60 degrees. If you look at B, so B is going in its own SHM, mean position. The particle B is at A by 2 and it is coming towards the mean. Meaning, see, it has already gone to the extreme and it took a turn backward. So if you are at A by 2, what is the phase angle? Sine theta is equal to half. Theta can be 30 degrees or 150 degrees. Since you're already coming back, meaning you have completed 90 and you're coming back, this phase angle is 150 degrees. Anyone don't remember this stuff, you should definitely go to SHM. And you should check out all this stuff. We spent a lot of time on this phase angles, if you remember. How do you get a phase angle at different points? I gave you that circle story also, if you remember. So we got the times and all. You should definitely revise that stuff. It's quite useful. Now see what happened. That means particle A ka phase is 60, particle B ka phase is 60. So what is the phase difference between them? So the phase difference between A and B is 150 minus 60. This is the meaning of phase difference. The two particles are doing their SHM, but they are at a different angles. This would be 90 degrees. And now we know the phase difference is k delta x, which is equal to pi by 2. K is nothing but 2 pi by lambda delta x. This is equal to pi by 2. Pi will cancel. Delta x is equal to lambda by 4. That means the distance between these 2 points was lambda by 4. So any 2 points with a distance of lambda by 4 they'll be always out of phase by 90 degrees. Means when you go to the extreme, I will be at the mean, and when you go to the mean, I'll be at the extreme. Is this clear, everyone? Are you getting the meaning of phase difference between two particles? So you know what is the phase difference per a particle. See, phase difference per a particle, that is you're comparing with the mean position. If you're at the mean position, see, this is how we did it, if you remember. If you're at the mean position and going to the right, your phase angle is 0. So phi tells you where you are with respect to the mean position. If you're at the extreme position, then your phase angle was 90. And I hope you understood how we got this. This thing came from that guy going in a circle, if you remember. When the particle was going on a circle, the shadow, so when you're here, the shadow was here. The phase angle was 0. When you're here, 60 degrees, the shadow was somewhere here. So the phase angle was 60. When you're here at the extreme, you haven't rotated 90 degrees, phase angle was 90. When you're here, you rotated this much angle, 120. So as you're rotating in a circle, the shadow is subtending an angle on the horizontal. So those are the phase angles. So this is the phase angle for a particle. Now what you're doing, you found this phase angle, you found this phase angle, and you're subtracting them. So you got a phase difference between two particles. Is that clear, everyone? So in an SHM, the phi always talked about the particle with respect to itself. When you say phase difference between two particles, you're comparing two different particles. Think of like this. It is like asking, how much did you score in the last exam? How much did you score in this exam? So I'm comparing your score with yourself, last exam and this exam. Phase the difference between A and B, how much did you score and how much did your friend score? I'm comparing between two different people. I hope that thing is clear, that wording is clear. So phase difference and phase angle of a point is different. So there. So if I know the distance between 2 points, I can find the phase angle, I can find the phase difference. And lambda is your wavelength. So that is like distance between two crusts and distance between two troughs. That is the simplest definition. Everything else, we have an idea. What is the wavelength? We know what is omega and everything. Let's do one question, and that thing should make things more clear. So let's say we have a wave equation, y is equal to 10 sine pi by 3x minus pi by 60. This is the wave equation. Find phase difference. So this wave is passing through a medium. Understand, when a wave goes, the particles really don't care. The disturbance is passing through a medium. In that process, the particles get displaced. The phase difference between x is equal to 2 meters and 7 meters. Find minimum distance between 2 points. Whose phase difference is pi by 3. Meaning, just to give a little more context, look at this scenario. The previous example I gave means after some time, the wave rate will actually become like this. So it will become like this. Matlab A will go to the extreme position. Then A ka phase angle will become 90 degrees. B will come to the mean position. B ka phase angle will become 180 degrees. But what is the difference between them? Still 90 degrees. Are you getting the meaning of that? A and B, their own respective angles will keep changing, but the difference will always remain same. Are you getting that? After some time, what will happen? A will come back to the mean position. As this A is going up and down, after some time, A will come back to the mean position. B will go to the extreme position. So A ka phase angle will be 180, B ka phase angle will be 270. The difference is still 90 degrees. Are you getting the meaning of this now? A ka angle will keep changing, B ka angle will keep changing, but the difference will never change. That is the meaning of phase difference. Yeah, get the Just formula substitution. Pretty straightforward. Some they do ask in mains also in bits. Question is not tough, but people get confused within phase angle of a particle and phase difference between two particles. So you have to be careful with that wordings there. So in SHM, you always studied one particle with respect to its own mean position. Yeah, got an answer. You can type here in the chat box. Yeah, what I taught you last class and a little bit of this thing. These things that is all based on equations. It looks a little weird, but this is the important stuff. Like you should know what is an equation thing like. The physical systems are actually easy and manageable. Let's see. Straightforward thing. First thing is what? Delta x is the part difference. So what is the difference between them? You said 2 meters. So 7 minus 2, that is 5 meters. So phase difference between the two particles is straightforward. 2 pi by lambda or k delta x. You can clearly see in this is k and this is omega. So that's what you should know the formula there. So k ka value is pi by 3 and that is 5. Okay, that's it, 5 pi by 3. The second thing, you want the minimum distance for the phase angle of pi by 3. So phase angle is pi by 2 pi by lambda delta x. That's pi by 3 is equal to 2 pi, or again, same thing, k delta x. K is pi by 3x. So delta x is 1 meter, meaning you take any 2 points with a distance of 1 meter, that angle will be always 60 degrees. Yeah, most of you did get it. Clear with this? That's an easy part. That's the phase difference between two things. Now let's see. This is a good one. So y is equal to 10 cos square pi by 3x minus pi by 60 plus pi by 6. This y here is a y coordinate. It's not the displacement. It's a y coordinate of a particle in a wave. So this is a wave equation basically. So find the amplitude. Find the mean position. Find the wave speed. Find lambda. Find the particle ka maximum speed. This is the max speed of a particle. Find the acceleration. Of the particle at x is equal to 2 meters and t is equal to 1 second. Find the phase angle. Yeah, get all of them. Just to give you an idea, what is the general equation? Y is equal to a sine kx plus or minus omega t plus phi. So you should convert this cos square like this, meaning you can actually write y minus y mean. If you remember, we did something like this. This is your more general equation. This y minus y mean, this whole term is displacement. So what's the amplitude? What is the v wave, phase angle, y mean, lambda, everything. So you have the equation, you have to get the data. So how do you convert this? So let's write your, yeah, that looks right, I think. So let's convert cos square. So you can write cos square as what? 1 plus cos 2 theta by 2. Hope you guys know that stuff. So y is equal to cos square pi by 3x minus pi by 6t plus pi by 6. So expand this. So cos square can be written as, there's a 10 also here. 10 into 1 plus cos 2 theta. That will be cos 2 times pi by 3 x minus pi by 6 t plus pi by 6 overall by 2. This can be written as 10 by 2. So this is y minus 5 is equal to 5. And you can write cos as sine 90 plus theta. Don't write sine 90 minus theta. I don't want omega to become negative. Then this will become 2 pi by 3 x minus pi by 3 t plus pi by 3 plus 90. Sine 90 plus theta is cos theta. And that 5 also I brought it this side. So y is equal to 5 plus. So bring that 5 this side. You get y minus 5 is equal to 5 sine 2 pi by 3x minus pi by 3t plus 5 pi by 6. There. So this is your mean position. So these particles are oscillating with 5 as a mean position. This is the amplitude. 10 is not the amplitude. The definition of amplitude is the maximum distance from the mean position. So the particle is going to 10, but your mean position is 5. So the distance between them is 5. Be careful. People write 10 and come. That's a straightforward CET equation. Find the amplitude. People write 10 and come. This is your K. This is your omega. This is your phase angle. You got everything you want. So what do you want to find? You want to find y mean. We got it. Amplitude. We got it. V wave. V wave is omega by K. You know omega. You know K. Substitute. You'll get the answer. We want V particle ka maximum. Do you guys remember in SHM what is the particle ka speed? What is the maximum speed of a particle in SHM? A omega. You can still use it here because these particles are still doing SHM, right? And what else you need? You need acceleration. Any ideas how to get acceleration? One way to do is double differential. So take that y. So v will be dou y by dt. Differentiate. Acceleration will be double differentiate dou v by dt. And then you substitute and you'll get an answer. There is a better way. Since the particle is going in SHM, can I write A is equal to minus omega square y minus y mean? Isn't that the relation between acceleration and displacement in an SHM? A is equal to minus omega square x. where x is the displacement. So this y here is your y coordinate. So y final minus y mean is the displacement. Omega ka value I know, y minus y mean I know. So this whole function I know. Yeah, you're done. Substitute there and then put the values of x is equal to 2 and t is equal to 1 and you'll get your answer. So if you do that, I think you'll get a is equal to omega square will be minus pi square by 9. That would be sine x is equal to 2. So if you put x is equal to 2, that will be 4 pi by 3 and t is equal to 1, that is pi by 3 plus pi by 6. I will leave it to you. You can solve that. So that would be like pi plus 5 pi by 6. So that's sine 180 plus 150. So that's minus sine 150. So minus minus half. I think you're getting pi square by 18, I guess. Check your answers. I'm not sure though. 25 you're getting? Yeah. Any doubts on this? All clear with this? So there, if I give you an equation, you can get all the data from there. You can get the particle speed, you can get the mean position, you can get everything. Any doubts on this? Please ask me. It's a pretty good one. We did something similar in SHM. It is a more simpler one though. Where is this guy? Yeah, look at this question. X is equal to 10 cos square pi by 3t plus pi by 6. And then I said find the amplitude omega, x mean phi. Same things. We did the same stuff. बस यहाँ पे एक extra kx आ गया था. And this will come again in AC circuits. So don't forget this. Idea will again come in AC circuits. All clear with this? So this is one way. I'll give you an equation. I'll give you an equation, get me the data. Second thing, I'll give you the data. You have to get me the equation. And this would be a good one. This will be an advanced come more than one choice question. So there is a wave going on and someone took a photograph. So this is a YX graph. I think before this, let me ask you an easy one and then we'll go there. This will be better. So we have a wave going there and someone took a photograph. There are 4 points, A, B, C, and D. It's a wave on a string. The wave is going forward. So this is the snapshot. Of a wave on a string. So the wave is going on a string and you took a photograph. Find the velocity, in which direction does A, B, C, D move? Options will be up, down, right, left. There'll be 4 options like this. Meaning at this instant, what is the direction of velocity of A, B, C, D? In which direction A, B, C, D move at this instant? Another decent question, not too tough, but you have to think about it. Is the question clear? So this is a wave on a string. You took a photograph. At this moment, how are actually A, B, C, D moving? What is the direction of velocity of A, B, C, D? You can go mathematically, or you can even do this thing you can even visualize this. Let me show you both. Options will be up, down, right, left. There'll be 4 options like this. So yeah, I think right, most of you did get it. So see, one way to do completely mathematical. If you guys remember, V particle is given by minus V wave into dou y by dou x, the slope. This was the relation. So this is Vy into slope. So at point A, the slope was positive. Point B, slope is negative. Point C, slope is negative. Point D, slope is positive. So if the slope is negative, means it is going up. So A is going up, B is this way, and this guy is also up, and this guy is going down. Clear with this? This is pure max. Like if the slope is negative, negative of negative, it is going up. V wave is anyway positive. So we have a negative slope. We have a this is a positive slope. This is a negative slope. This is also a negative slope. This is a positive slope. But there's a better way to do this. Huh? Listen to this. How is the wave going? Right side, right? Do one thing. Next moment, what do you think will happen to the wave? This was your entire wave pulse. Next moment, if I let the wave go little forward, you let push the wave little forward. So if you push the wave little forward, the wave will look like this. Do you guys agree with this? So this red thing, the wave has gone little forward. Now look at this clearly. A will always go up and down. So this A will come to this wave, and this B will go to this wave, and this C will go to this guy, and D will come to this thing. Can you clearly see how they're moving? Just push the wave little to the right and see how it would happen. So all these positions, right, should be on this red line now. So that means A has gone from green line to red line. B has gone from this green line to the red line, and the C has gone from the green line to the red line, and D has gone from green to red line. This is more pictorial way of figuring it out. You just push the wave little forward and see how it moves. But in case that doesn't strike to you, yeah, mathematically you always have this formula. Is this understood? All clear with this? Great. Any doubts on this? Clear, na, Amrita? Clear with this? Tanishka? Vedika? Shreyansh? Perfect. Let's see the next one. This is a YX graph. So someone took a photograph of a wave. This point to this point, this distance is 2 meters. A particular point here, P, is going up with a speed of 4 meters per second. And at this point here, this angle is 60 degrees. This height here is A by 2, half of the amplitude. So this is the snapshot of a string at T0. So when a wave is going, someone took a photograph, and this is all the data you have about the thing. Snapshot of a wave at on a string at T0. And particle ka maximum speed is given as 10 meters per second. I should take everything in centimeters, but okay. Numbers are like, yeah, too much. This is all the data you have. You have one photograph and you know the maximum speed. Find the wave equation. In case you're confused, what you need to find, the wave equation will be like this: y is equal to a sine kx plus or minus omega t plus phi. So you need to find y mean is 0. You need to find a ka value, k ka value, is it plus or minus omega ka value and phi ka value. If you can find these 5 values, your job's done. Get them. This is a photograph, and you know the maximum particle speed. Find the wave equation. Let's see what you can figure. Whatever you can from the picture, whatever data you can figure out. Did you guys figure out the wavelength? That is the easiest part. You can clearly see half wave is 2 meter, meaning this is lambda by 2, right? One full wave is lambda, half wave will be lambda by 2. So you know lambda from there. Think. I'll give you a minute more. Yeah, get the remaining also, na, Srihari? Get the rest. Think. It's a good question. Like, frankly speaking, if you see all the thing that I taught you for last 1.5 class, right? Like, you can say it is all about this question. Everything has come together. So till now, whatever I taught you in the last 1.5 class, I think this is the only question which is little worthy of an advanced question. Nee, Ishman, you did fall into the trap. Nee, Srihari. Harshita, I think you got it. You figured it out. That 5-phase angle was a trap. Try. Another 1 minute and then I'll show you the whole thing. It's a good one. See? Okay, that's it. So first thing, you can clearly see the wavelength was lambda by 2 is 2 meter. This guy was lambda by 2. So lambda by 2, 2 meter. From here I got lambda, which is 4. From here I got k ka value 2 pi by lambda, which is pi by 2. So k ka value aa gaya. Perfect. Next thing, we also know V particle is equal to minus V wave into slope. Slope is nothing but, so V particle is going up 4 meter per second minus V wave. Slope is how much here? Tan 120. It's not tan 60. Theta should be taken with the positive x-axis. So this is 4 is equal to minus V wave and tan 120 is root 3. So we got V wave is equal to minus 4 by root 3. sorry, minus root 3. So this is 4 by root 3. So plus indicates it's a right traveling wave. So this is plus. That means beach mein you have a minus sign. This is a right traveling. If you had got a minus sign, it's a left traveling wave. So that equation will tell you which way the wave is traveling also. So the function should be kx minus omega t. If it had been a minus thing, that would have been this way. And then what is v wave? We also know v wave is nothing but omega by k. I already know k ka value. I know this thing. I'll get omega from here. Omega will be k into v wave. And it is also given particle ka maximum speed. So Vp max is nothing but a omega. I know a Vp max and I know omega. I'll get amplitude from here. I got everything except phase angle. Please have a look at this. This formula is really important. V particle is minus V wave into slope. Most ignored formula. People don't remember that, but it's quite useful to find the particle speed and wave speed relation. Now, when it comes to the phase angle, this is the most common mistake. People see, oh, it is at a by 2, so 30 degrees, pi by 6, and that's when you get trapped. So if the particle is at a by 2, is the phase angle always 30 degrees? How is the particle actually going? Now, this is the reason I taught you the previous question. Ask yourself, how is the particle actually going? Initially, it was like this. This was the wave, and the wave is going forward. Meaning next moment, what will happen to the wave? Next moment, the wave will become like this. The green one. It is pushed forward. That means this particle here is not going up, it is coming down. The particle at the origin is actually coming down. And you're at a by 2 and you're coming towards the mean position. So that means this particle has gone up and you're coming back. And you're at a by 2. What will be the phase angle then? 5 pi by 6. Is that clear, everyone? So there'll be two options, one with pi by 6 and 5 pi by 6. Most people in a hurry will put pi by 6 and come. If the wave was going backward, then the wave would have been like this. Then the particle had been going upward. Did you see? So depending on which way the wave is traveling, the phase angle will change. So be careful because this is a photograph. In a photograph, you don't know how the wave is going. The wave could be going forward or the wave could be going backward. We don't know that. And based on which side the wave is going, the phase angle does change. Any doubts on this thing? Do ask me if you're confused with anything in the data there. All clear with this? The phase angle part was here. There, that's a bit about the wave equation. So we have studied what is a wave, we have seen a wave equation, then we have said like we will study only sine waves henceforth. And we saw from a photograph, you can get a wave equation. If I give you an equation, you can get the data. The next part is the wave speed. Now we kept on saying waves on a thing. So first thing we will study transverse waves, waves on a string. So we will study waves on a string separately, then we'll do sound waves back after this. But everything that you learn here, ideas will be quite similar. Now we will not do the derivations. Derivations are not that important for the wave speed. Because there is one very classic derivation which is not exactly right, and there's one very complicated derivation which we don't require. It's a waste of time. We will not do it. So this is the wave speed on a string. So if you take a string and if you generate a pulse, so how fast this pulse will travel will depend on the tension. So this is the main formula which you need to write down. V wave is equal to root over T by mu. T is the tension in the string. So if the string is very tight, it will go faster. This mu is not friction. It is actually mass per unit length, lambda. So if you remember, which we used in center of mass and everything. Why are we not using lambda? Because we already used lambda for wavelength. Yeah, so unfortunately, we don't have enough symbols. So mu is nothing but linear density. This is kg per meter. This is the mass of a string per unit length. There. This is the main formula, everyone. Yeah, technically, that is the only concept there for a wave speed. But be careful. This wave speed is with respect to the string, not with respect to the ground. This is the wave speed with respect to string. Example, let's say we have a truck. The truck is going with 20 meter per second. Inside the truck, we have a wave pulse. The wave is going with 2 meters per second. So then the wave speed in the ground frame is actually 22. So this formula gives you wave speed with respect to the ground. It's like 2 plus 20. So if the string itself is moving, then your wave speed will be different. If you have the last thing that I showed you, right? That I hope you went and played in the website which I showed you. So so look at this. So there. So this was the same thing that we did. Let's put damping here. Look at here at the bottom here. You can see something. There's something called tension. So I can increase or decrease the tension. So if I decrease the tension, the string is pretty loose, and if I generate a pulse, there's an amplitude. I can give a amplitude here, and I'll see how it is traveling. And now same thing. If I increase the tension to full, and if I just send the pulse now, it goes pretty fast. There's a little lag, but you should check out this thing. I did post the link in the last class, so you can play with this. You will notice this thing, if you take a string and attach it to the wall or something, and if you keep the string tight and then you generate a pulse, it travels pretty fast. So that's it. So main thing, if you look at this formula, right, if you know how to find the tension, your job's done. So let's see a question on this. We got a rod here. You tied this with two strings, mu and a mu. Mass of the rod is m and length L. You attached a block here of mass m at a distance of L by 3. Now what you did, you generated a pulse on this string and generated a pulse on this string. So this is V2 and this is V1. So a rod is hanging from a ceiling and the waves are generated on the supporting strings. Is the story making sense? We took a rod of mass m length L, you took a block of mass m, attached it here. The two strings which are supporting this system, they're tight, right? The string tension is there. You're generating a pulse there. So waves are generated on the supporting strings. Find V1 by V2. Both the strings have same mu, mass per unit length. So if you know how to find the tension, root T by mu, direct formula substitution. Give it a try. I hope the picture was clear. Anyone not clear with the picture, please ask me. Let's see. This is actually mostly a rotational mechanics question. You just need to find the tensions. Step 1, draw the free body diagram. What are the forces? We have tension T1, we have tension T2, your own weight mg, and this block ka weight mg. That is your tensions there. Since it is in equilibrium, T1 plus T2 is 2 mg. Since it is not rotating, take torque about any point. I'll take torque about A. So torque about A is equal to 0. If we take torque about A, that will be T2 into L must be equal to mg into L by 2 for the center of the rod plus mg into L by 3 for the block. This will give you T2 is equal to 5 mg by 6. If T2 is 5 mg by 6, then T1 will be 7 mg by 6. This is a pure rotational question. You're done. Once you got the tension, the wave speed ka formula is root over T by mu. So V1 by V2 is equal to root over T1 by mu by root over T2 by mu. So V1 by V2 is T1 by T2. T1 by T2 is root over 7 by 5. Once you know how to find the tension, question is over. It just you have to substitute in the formula. All clear with this? Yeah. Right, Anvita. Right, Samyak. Right, Nisha. All clear with this thing. Rotational mechanics, torque ka question. Let's see one more. We got a disk circular ring which is rotating with omega. Another standard question. So this is a ring of mass m and radius r rotating with omega. Neglect gravity. Now what you did, you hit the wave, you just disturbed it, and you got a bump here like this. Now see, this bump can travel this way, this bump can travel this way. It can both the waves. Find the wave speed with respect to the ground. So because the ring is rotating with omega, there'll be a tension in the ring. Hope you guys remember this thing I told you comes multiple times. I think almost it comes in 6 times. If a ring is rotating with omega, it has a tension inside. And then what you did, you have gently give a bump on that rotating ring, and this bump starts traveling around. It can go left or right. So find the wave speed with respect to the ground. This first time it came in circular motion. Then you saw this in elasticity. Then you saw this thing in surface tension. You saw this thing at multiple places, and you should not forget this. Uh, this is the question if you guys remember. There. A ring of mass m and radius r is rotating with omega. Find the tension in the ring. So basically, when the ring rotates, the centrifugal force is pulling the ring away from the center. So this generates tension in the ring. Page 59, circular motion. Do you guys remember this? Take a small piece, 2t sine d theta by 2. This is the story. So I'll put the reference there. Page 59, circular motion. This is actually a circular motion question. I should definitely refer this. But anyways, let's derive this. So when you look at the top view, this was the ring. Take a very thin slice. This is very small d theta. I'm going to exaggerate this, so I'll take a big thing here. So if you drop a bisector here, so this angle will be d theta by 2, and this angle will be d theta by 2. If you look at the forces, this will be tension, this will be tension, and the centrifugal force is dm omega square r. This angle here will be d theta by 2. You can check it out from geometry there. So we get 2 times t sine d theta by 2 is equal to dm omega square r. For small angle, sine theta becomes theta. So that becomes d theta by 2. dm is nothing but total mass by total length m by 2 pi r into the length, which is r d theta. That is your dm. That is the mass of that small piece. From here, we get tension is equal to m omega square r by 2 pi. Standard result. Once you got the tension, then we put it in the formula, wave speed, which is root over t by mu. So tension is m omega square r by 2 pi. Mu is nothing but total mass by circumference 2 pi r, which comes out to be r omega. So wave speed, we got r omega. But be careful, this is not the answer, because uh, this is the wave speed with respect to the ring. So we got wave speed with respect to the rotating ring is r omega. Now there are two possibilities. If the wave is traveling this way, r omega, and your wave is also traveling r omega, the speed will add up. That will be 2r omega. But if the bump is traveling backward with r omega, and the wave itself is going this way r omega, the wave speed will be zero, meaning for a person, it will think the bump is there only. It will feel the bump is at rest. You're getting it? So the pulse will remain stationary in the ground frame. So since they didn't tell you which way, both are right answers, depending on which way the pulse is traveling. So be careful with that. The answer is not r omega. The r omega which you got is in the Rinka frame. Right, Naisha. Right, Utsa. Got it. Right. Samyak, you got the relative speed. Ovia, yeah, you also got the relative speed. All clear with this? Any doubts on this? So there, so we see the main thing is that if you know how to find the tension, your job's done actually. 70-80% job is done. The tension will come from different chapters. Let's see. We have a rope here hanging from the ceiling. Let's say mass of the rope is m and length is l. Gravity is there. What you did, you generated a pulse at the bottom. Right? Um, find the time taken for this pulse. So the pulse is going up the thing there. Find the time taken for the pulse to reach the ceiling. This is a standard mains question. Direct result. And they did ask multiple times. But we'll see a better one than this. But find the time taken for the pulse to reach the ceiling. This question 8, right? And this is a very good set of questions. So there is a string hanging from the ceiling. Now, what is happening as you go up, the tension is increasing, isn't it? The higher you go, the more tension you have. The speed is not constant. Find the time taken for the pulse to reach the ceiling. And remember, there's only one formula you need. V is equal to root over T by mu. So how do we do this? First, let's find the tension. So if you take the rope here at a distance x from the bottom, see if you cut it here, the tension at this point is because of the weight of this rope, isn't it? And what is the weight of this rope? Mass m by L into x, that is the total mass into g. So tension in the rope is mg x by L. So tension is not constant. As you go higher and higher, tension will keep increasing. So what is the wave speed curve formula? Root over T by mu. So T is equal to mg x by L. And what is mu? M by L. This is root gx. Perfect. So we got this speed, right, is increasing with gx. So differentiate, integrate dx by dt is equal to root gx. Bring it this side, we get dx by root x is equal to root g dt. 0 to L, 0 to T. This thing will be x power minus half. So that will be 2 root L is equal to root g into time. So T is equal to 2 times root L by g. Then one integration and you're done. So find the tension as function of x and finish it off. There is a more interesting way. We know v is equal to root gx. If you square on both sides, we get v square minus 0 square is equal to 2 times g by 2 into x. Can I write like this? This guy is looking like v square minus u square is equal to 2as. It's looking like that. So what you get is, interestingly here, the acceleration of the pulse is g by 2. So the pulse is actually going up with a constant acceleration. That itself is another good question. So when you send a wave on a string like this, which is hanging, it behaves as if it is going up with a constant acceleration. So acceleration of the pulse is constant. Then I can use s is equal to ut plus half at square. S is L, u is 0. Acceleration is g by 2, t square. We get t is equal to 2 into root L by g. Same answer. So this is another good result. So acceleration is g by 2. Everyone clear with this? So when you take a string which is hanging from the ceiling and generate a pulse, they actually move with constant accelerations. Take a break, come back in 5 minutes. Come back by 9:47, we'll continue from here. Chalo, camps on everyone. So we got a rope here hanging from the ceiling. Now, this is a rope with a variable density, mu naught into x power n. N is some constant. So n is some number there, right? And mu naught is a constant. So look at this thing, x power n. So it could be x square, x cube, x power 100. It could be anything, x power root x, anything. N is not equal to -1, but it can be any other number. So, so the density is varying. Now you send two waves. You sent a wave from the bottom, you sent a wave from the top. So both the waves are coming towards each other. So first thing, find the acceleration of the pulses. So this is a better one than the previous one. If you put n is equal to 0, it becomes the previous question. But the previous question is a proper mains and bits level question. It has been asked multiple times and it does keep coming. It keeps coming repeatedly. Find the position where the pulses meet. So where will these two waves meet? There, let's get this. Same as the previous one, I just made the thing rope with variable density. Yeah, right, Samir. Same story. You need to find the tension. That is the main story. If you get the tension, your job's done. That's actually a little headache here. So how do you get the tension? So look at this. Somewhere here. So at a distance x from the bottom, take a small slice dx. So if you take this small slice dx, what are the forces acting on this? We have tension T plus dt, and we have tension T. So the tension will increase by small amount dt because of this small guy, and the weight will be dmg. So from here we can clearly see dt, the extra tension is because of the small weight dmg. And what is dm? dm is nothing but a mu into dx. But what is mu? Mu is mu naught x power n into dx into g. Integral is on both sides. So dt is equal to mu naught g integral x power n dx. What is the tension at the free end? This thing I told you multiple times. Free ends will always have zero tension. If an end is not attached to anything, they will not have any tension. free ends and free surfaces will have zero tension and zero pressure. So at x is equal to 0, tension is 0, which is not true every time. x0 t0 हर बार नहीं होगा. So this is 0 to x and this will be 0 to t. So from here I got tension is equal to mu naught g x power n plus 1 by n plus 1. So this is the tension at a distance x from the bottom. That way. Or you can even say at this point, you can take a small element dy and integrate all the masses and say this is the tension. You can do it however you want. And once we got this, we know what is the wave speed ka formula. V wave is nothing but root over t by mu. This will be mu naught g into x power n plus 1 by n plus 1, and mu will be how much? Mu naught into x power n. Mu naught will cancel, x power n will cancel. You end up with root over gx by n plus 1. Check it out. That's your wave speed. Like I said, the actual question is about finding tension. The wave speed formula, there's nothing. You just, once you get the tension, dump it there and you're done. Let's see the position and time. Any doubts on this integration here? Right, Utsa. Most of you did get it. Ashita got it. Samyak got it. And now if you look at this velocity, v is equal to root over gx by n plus 1. You want to find acceleration, we can do v dv by dx. But there is a better way. Square it on both the sides. V square minus 0 square is equal to 2 into g by 2 times n plus 1 into x. If you see here, this guy looks like v square minus u square is equal to 2as. You can get it from v by dx also. So we get acceleration is equal to g by 2 times n plus 1. If you observe, this is a constant. It doesn't matter whether what is the x power n there. You got a constant acceleration again. Even though the density is changing, a is constant. So that's one good thing. All clear with this? So perfect. So we got the acceleration of the pulse. That means on this string, any pulse that you generate will have a constant acceleration. Now coming to the question. So that string, what you did, you generated 2 wave pulses. So this guy is coming down. So this will have some speed here, which is v1. And what is the acceleration? And this will have some speed here. That will be, let's see. So this will have an acceleration a backward, and this will have an acceleration a forward. And this will have some speed v2. So the tension at the topmost point you just need to put x is equal to L here. Or you can say wave speed at the top, v is equal to root over g into x by n plus 1. This is your wave speed. So the difference between the two pulses, right, is this. This pulse ka speed is not 0. Initially, it has a speed v1 is root gl n plus 1. Here v2 is 0. Now see, this question has become like this. We have two waves. This wave ka initial speed is v1. This wave ka initial speed is 0. This wave is decelerating because see, as you come down, tension decreases, so speed decreases. So it thinks it is decelerating. This wave at the bottom is accelerating. This whole equation has become as if like a projectile motion. We have two particles. This guy is coming down with v1 and this guy is starting from rest. And this guy has an acceleration up and this guy has an acceleration up. And the question is find the time when the two particles meet. The question has become like this. We can use relative motion. So if you use relative motion, then what do we get? So we get v relative is v1 and a relative is 0. That is the interesting part. Since both the accelerations are in the same direction, a relative is 0. And this length is L. So we can directly use the formula S relative is equal to U relative into time plus half A relative time square. So S relative is L, U relative is V1 and time. So this is the time when the waves will meet. You can make this question into kinematics. Is this making sense? The two pulses will behave as if they have a constant acceleration, right? So they will behave like, as if it is a constant stop time. There you got the time. So this is the time when both the waves will meet. And what are you asking? So when they meet somewhere here, so they will meet at time t here. Then I can come back to the ground frame. So what is this distance traveled? So this is the position where they meet. So S is equal to V2 to E plus half A T square. V is 0. This will be half acceleration, which I know, which is this guy, G by 2n plus 1. Plus this time I know, which is L square by V1 square. Substitute there, you get the answer. So the waves will meet at a distance S from the bottom. Are you clear what we did, everyone? So do you guys remember this kind of questions in kinematics? There is a building, one particle A is thrown down, one particle is thrown up. Find the position where the two particles will collide. Yeah, is that questions? The only difference there was gravity used to be down. So यहाँ पे the gravity is up. So we can stop one of the wave. You get B relative, you'll get A relative, and you can solve the problem with kinematics. Huh, Vedika? Is that making sense? We found the wave speed of this guy, V1. We found the wave speed of this guy, V1, V2. These are initial speeds. Acceleration A, same direction. So what is V relative? V1 minus 0. What is A relative? 0. Means both the waves will think the other guy is not accelerating. So what is the time taken? The distance between them, which is L, is equal to V into T. We got the time. Now, if you come back to the ground frame, you think this pulse is traveling upward with an acceleration A for this much time. S is equal to half AT square. Clear with that? So maybe I can do it in the next page if you guys want. That looks confusing. So we got the time. So this is the time when they're meeting. So now again, if you come back to the ground frame, so this pulse has initial speed 0 and acceleration A. So they will meet somewhere here. So S is equal to half AT square. Yeah, you can substitute the V1 ka value, and that will be how much GL by root n plus 1. N plus 1 gets cancelled. G also is getting cancelled. You're getting L by 4 there. They're meeting at a distance of L by 4 from the bottom. So the first part is to figure out they have a constant acceleration. Second part is to get the initial velocities. Now the question has become kinematics. Everyone clear with this? So first you'll find the tension as function of x, and then you use the wave speed, then we get the acceleration, then we use kinematics. Any doubts on this? That's a bit about the wave speed. So you can keep playing around. So main idea is always that you have to keep finding tensions, put it there, and you get a wave speed. Next thing, if you have a wave speed, then you also have energy. So energy in a progressive wave. Listen to this carefully. You can get really good theoretical questions on this. Now, when a wave is going on a string, this is the natural length. See, I'm exaggerating the figure, but in reality, the amplitudes will be in millimeters, 2 millimeters, 3 millimeters, and so on. So this dotted line is the natural length of the string. If there is no wave, the string would have been flat like this, the dotted line. But when the wave starts going, the string actually starts stretching. So these are not ideal strings. In an ideal string, it doesn't stretch. In an ideal string, you can't send a wave. Now observe the the point which is at the peak. If you look at here, the slope is 0. So if this length is dx, this length is also dx. So the particle at the extreme position is at the natural length. So the small segment dx at extreme position is in natural length. So that part, when it goes to the extreme position, it is not expanding or compressing. So therefore, the elastic potential energy is 0. So be careful. In a wave, when you say potential energy, we are not talking about gravity. We are talking about elastic potential energy. So elastic PE is 0. Since you're at the extreme position, kinetic energy is also 0. Since at extreme, the kinetic energy is 0. That means the segment of a string, which is at the extreme position, has no energy. It has no potential energy, no kinetic energy. Similarly, if you take a segment at the mean position, so this segment here, you can clearly see it got stretched a lot. So here, the elastic potential energy is maximum. At a mean position, speed is maximum, so kinetic energy is also maximum. So the segment at mean position, the elongation and speed both are maximum. So if you observe here, energy is not conserved. Energy is not supposed to be conserved because, do you guys remember the definition of a wave? In a wave, energy and momentum are transferred. Energy is continuously moving forward, isn't it? So energy can't be conserved. It has to keep moving forward. So what is happening here exactly? See, next moment, what will happen? This wave, right, will come down like this. So the wave, as it goes forward, after some time, it will become like this. It will become like this. Now see what happened. This position at the extreme has come to the mean position. The particle at the mean position has gone to the extreme. So this particle energy becomes maximum. This particle energy becomes 0. Can you see what is happening? So every time it goes to the mean position, it will lose energy. Every time it comes to the extreme position, it will lose energy. When it comes to the mean position, it will gain energy. So the particles are gaining and losing energy. Energy is not conserved on a string. This is the first time you're seeing something like this. Till now, what you used to see? Potential energy 0, kinetic energy maximum. Kinetic energy 0, potential energy maximum. This is the first time you're seeing both are 0 and both are maximum. So a segment, this is for a segment, okay? A small piece. A segment at extreme position. This is a good theoretical question. The potential energy is 0, kinetic energy is 0. Just to be careful, when they say potential energy, we are talking about elastic potential energy, not the gravitation. A segment at a mean position, potential is maximum, kinetic energy is also maximum. So energy of a segment is not conserved. So when a wave is going on a string, every point the energy is continuously changing. Energy is not constant. Is this clear, everyone? This itself will be a good theoretical question. Simple question. Which of the following options is right for a segment at an extreme position? Potential energy 0, kinetic energy 0. Potential energy maximum, kinetic energy maximum. Potential energy 0, kinetic maximum, potential energy maximum, kinetic 0. बस हो गया 4 options. Most people will think one is 0, other is maximum. So simple thing, but it's a theoretical thing. Clear with this? So this is the theory part of it. But let's try to calculate the value. Now this stuff is important for advanced. Mains may they will not touch this. For mains, this page is sufficient. They will not go beyond this. But advanced may you need to know a little more. So let's try to find the potential energy for a small segment. First, I'll write the formula and then I'll give the derivation for this. It's not really that important, but let's see. Again, remember, this is elastic potential energy of a segment dx. This is given by half into tension dou y by dou x whole square into dou x. This is the potential energy of a segment, and this guy is valid only for small amplitudes. Let's see how we got this. Something like 1 millimeter, 2 millimeter, something of that sense. So let's say we got a string here. This was the natural length. So consider a small segment here, dx. Again, I'm exaggerating here. So, and this is theta. So this small segment here got stretched into this big piece here, which is dx by cos theta. So you can treat that segment has become dx by cos theta. So dE is elongation in the dx piece. So when this wave is moving, it will stretch. So this will be dx by cos theta minus dx. So this is the elongation in that small piece, which can be written as dx sec theta minus 1. So it used to have a length of dx. Now it became dx by cos theta. So work done by tension will be tension into elongation, because the tension is almost constant. That will be T into D. That would be T into dx into sec theta minus 1. Sec theta can be written as root over 1 plus tan square theta. So that is 1 plus tan square theta whole power half. Since the amplitude is small, theta is also small. That's the whole point of taking small amplitudes. The amplitudes are big, you can't use this derivation. So theta is small. If theta is small, then you can use binomial approximation and tan theta becomes whatever it is. Then tan theta is small. So this will become T into dx. This will become 1 plus half into tan square theta minus 1. 1 will cancel. You end up with half into T into dx, and tan square theta is nothing but dou y by dou x whole square. That's the formula for energy for a small segment. And work done by tension is nothing but change in potential energy. Derivation is not important. The result is more important. Even at an advanced level, derivation is not important because it has so many approximations, they won't touch it. But for small amplitudes, that formula really works. So half tension, dou y by dou x whole square, which is the slope into dx. Clear with this? So that is how you get it. You take a small string dx, and let's say it got stretched by dx by cos theta. So we are treating that like a hypotenuse because theta is small, and then we got the elongation and tension into d. All clear with this formula there? Now, second thing, the kinetic energy. We also have kinetic energy for the small segment. This is actually the easier one. What is the kinetic energy for a segment? Half into dm into v square. What is dm? Half into mu into dx. And what is v square? Dou y by dou t whole square. There. So kinetic energy of a segment is half mu. Mu is your mass per unit length. Dou y by dou t whole square into dx. This is your kinetic energy. And you will see something interesting here. So this is the formula for kinetic energy, but this is the easy way to remember half dm v square. You can get it. But we also know v particle, which is equal to minus v wave dou y by dou x. So v particle is nothing but dou y by dou t, which is minus v wave dou y by dou x. So if I take this and substitute here, see what you get. With kinetic energy of the segment dx will be half mu. This guy will become v wave square dou y by dou x whole square into dx. But what is v wave square? V wave square is nothing but root over tension by mu, which is T by mu, which is dou y by dou x whole square into dx. Mu will cancel. You end up with half into tension dou y by dou x whole square into dx. which is nothing but potential energy of the segment dx, which is the kinetic energy of the segment dx. So the kinetic energy and the potential energy for every segment on a progressive wave is same. Are you clear with this thing? That is the reason. See, when both are zero or both are maximum, they both go together and come down together. All this stuff, right, are pretty good theoretical questions. So they'll ask you, how does the potential energy and the kinetic energy vary? They are actually exactly the same values there. They're equal. All got this? So just let me put down the final thing there. So potential energy for a small segment dx is half into tension dx dou y by dou x whole square. Kinetic energy for a small segment. So even if you don't remember the potential energy thing, it is easy to remember the kinetic energy thing. Half mass mu dx velocity is dou y by dou t whole square. So you just need to find the kinetic energy and double it. That will become the total energy. These two guys are equal. That is the best part. So that means we can write the total energy is potential energy plus kinetic energy, which is 2 times the kinetic energy of a dx. This is the total energy of a small segment dx. All clear with this? You can put on that formula if you need. We are going to do a question on that you might need. Let's say a question on this. We have a triangular pulse which is going on a string. The speed is v, mu is your linear density. This height is a, and this whole length is L. And A is much, much smaller than L. So the amplitude is very small. So the triangular wave is going, a triangular pulse is going on a string. So someone generated a pulse like this. Find that energy of this pulse. So the amplitude is small with amplitude A and wave speed V. Find the energy in this pulse. So there will be some amount of energy stored in this pulse. How much energy is traveling forward? Find the kinetic energy and potential energy of the pulse. Or I can ask you total energy, which will be the sum of them. There, give it a try. These are the kind of questions they'll ask you. This will be good advanced questions. So if you don't know that P, dx and kinetic energy for dx, you can't solve these questions. You can copy down these formulas if you need. You should remember them. It's okay if you don't remember the derivation. Let's give it a try, everyone. So how do we start? Uh, so this angle is theta. So we get tan theta is A by L by 2, 2A by L. Remember, this is dou y by dou x. This is the slope. Perfect. You want kinetic energy? And we also know this relation. Dou y by dou t, that's your particle speed, is equal to minus v wave dou y by dou x. So dou y by dou t is minus 2ab by L. Yeah, you got everything you need. So what is the kinetic energy for a small segment? Half mu dx dou y by dou t. But what is dou y by dou t? 2ab by L. So this will be half mu 4a square v square by L square into dx. Integrate this. So kinetic energy of the pulse will be 2 mu a square v square by L square integral dx from 0 to L. 2 mu a square v square by L. That's the kinetic energy of the pulse. And we know kinetic energy of the pulse will be equal to the potential energy of the pulse. You can check if you want. You'll get the same thing. And you're done. The total energy will be double of this. How do I know it is equal? Understand one thing. When I proved these two are equal, did I even take what is the equation? Did you see when I proved it, did I take y is a triangle function or y is a sine function? I proved they're equal for any random function. So whether it is a triangle or a sine, it doesn't matter, it will work. So you can just find the kinetic energy and double it off. No, you want to do potential energy, you can do it. So potential energy will be half into tension into dou y by dou x whole square. How do you write tension? V wave is equal to tension by mu. So from there you get the tension, substitute here and solve. You'll get the same stuff. Is this clear, everyone? It's a pretty good question. This one, the previous one, you should definitely give them a try again. These things are a little non-standard there. The next thing, now let's get back to our standard regular wave. So for a sinusoidal wave equation, your y is equal to a sine kx minus omega t. This is your standard equation. And if you try to substitute here, the potential energy of a segment, PE dx, the formula would be this, half tension dx dou y by dou x whole square. Remember, dou y dou x is partial differentiation. And we also know V wave is equal to root over T by mu. So tension will be mu into V square. So substitute here, half into mu into V square into dx, and dou y by dou x will be A into K cos kx minus omega t ka square. So when you differentiate with x, time is constant. So the potential energy for a segment dx turns out to be mu half mu, and we also know V is equal to omega by k, or V square into K square is equal to omega square. So V square K square will become omega square half mu A square omega square dx cos square kx minus omega t. This is your kinetic energy changing with x and time. It's not constant. Can you see how it is fluctuating? It's a cos square function. So if they ask you find the potential energy for a segment somewhere, this is how the thing is varying there. Same thing if I do for kinetic energy. I know it will be equal, but let me prove it. So half mu dx dou y by dou t whole square, half mass into velocity square. So dou y by dou t square, partial differentiation with respect to time, you end up with A into omega cos square cos kx minus omega t whole square. Expand this and you'll observe half mu A square omega square cos square, exactly same thing. See, the kinetic energy and the potential energy, they are exactly the same function. They're always equal. That's why both go to maximum and both go to minimum. This is the kinetic energy and potential energy for a sinusoidal function. Clear with this? Now, if you want to find the total energy of a segment, we add them. The total energy for a small dx will be potential energy and kinetic energy. We just add it up. So we get the total energy for this small segment dx will be double this. So we'll get mu a square omega square v wave dx cos square kx minus omega t. This is the energy of any segment, which is not constant, which is changing with time. And we know what is power. Power is nothing but energy by time. So this will be a small energy dE by dt. This will be mu a square omega square dx by dt cos square kx minus omega t. And dx by dt is nothing but wave speed. So this is the instantaneous power. So this much power is passing through the string at any instant. Dx by dt is nothing but wave speed. So mu a square omega square v wave cos square kx minus omega t. So when someone is generating a wave, they're sending this power every instant. And we know the average value of a cos square function is half. If you take for one cycle, average of cos square theta is half. So if you find the average power, this is the formula you'll find in all the books. They'll give you the average power passing through the string, which becomes half mu into a square omega square v wave. That's the standard formula you'll see in everywhere, and that is how it's derived. So that's the instantaneous power, and this is your average power. Yeah. So mains perspective, the average power is the formula you should definitely remember. Instantaneous power, if at all they ask you, I'm not sure. They might put it in a paragraph, or it might be a theoretical question or something. I have never seen them asking before. So could be in some way, someday it will come. So I'm sure if you have done this chapter before, you must have seen this formula. That's how you got this. You should definitely remember that thing. Half mu a square omega square v wave. All clear with this? I know a lot of math, a lot of differentiation, that, this, but try to do it on your own once more. It will help you a lot. It's a very good discussion. Energy of a wave. Now here we also define something called intensity. Intensity is nothing but power by the cross-sectional area of the string. How much power is passing through an area? So this will be half mu by area a square omega square v wave. And this is one more thing. So when we know mass m can be written as density into volume, or let's say you can write density rho is mass by volume. You can write volume as mass by area into length. So this can be written as mu by L. Mass by L becomes mu by area. So this mu by area becomes rho. So intensity formula is half rho a square omega square v wave. Be careful, rho is your volume density, mu is your linear density. Power P ka formula was half mu a square omega square v. They both kind of look same. The only difference is mu and rho. So people do goof up between intensity and power. They look same, but they both are not same. So these are the final formulas you need to remember for mains and bits. So rho is volume density. Mu is linear density. So you can have two copper wires. They'll have same rho, But if their area is different, they can have different mu. You can have a thick wire and a thin wire, and you can have different mu's. All clear with the stuff? Let's do one question on this, and then that's the energy part there. So we got a tuning fork here of frequency F, and you attached a string here, and this is basically so we got a pulley here, and we got a block here of mass M. We got a tuning fork F here, and we got a block here of mass 2m. This thing has an amplitude A. This thing has an amplitude 2a. It is a density rho and radius is r. R is the radius of the wire. And this thing has a density rho, but the radius is 2r. F is the frequency of the tuning fork. Both are same frequency. And the right side, the block is M and the block is 2m. So these are generating the tension in the string. So these are the blocks are keeping the strings tight. Amplitude A, amplitude 2a. Density is same, R is this. Find the ratio of power transmitted. So how much power is passing through this string and how much power is passing through this string? Average power. If they don't say anything, it is always average power. Find ratio of power transmitted. In case you don't remember, you can just note down this formula. Half mu A square omega square V wave. That's the formula. So when you take a string and you generate you're generating waves, this is the power that passes through. There, let's give it a try. I literally changed most of the details there. So it's just a matter of formula substitution, but you have to be careful. Today's class is math heavy. You should definitely give it a try. So what is the catch? Let's see whether you remember. Do you guys remember if you keep a tuning fork like this and like this, it is different? What was the difference? This one, remember? If you keep the tuning fork like this, you get the same frequency of the tuning fork. But if you keep it like this, you get double the frequency. Yaad aaya? We did this thing in the last class. So they're not generating same frequency. So here, the frequency of the wave is F. Here, the frequency of the wave is 2F. Even though the tuning fork is same, depending on how you keep it, it will change. Second thing, rho is nothing but mass by volume. Volume is nothing but mass by area into length. Mass by length is mu. So rho into area is equal to mu. And that is nothing but rho into pi r square. So that is a relation of mu. So they don't have same mu. And second thing, in the string, if this is tension, this is mg. This is tension, this is 2 mg. So they don't have same tension. So tension is different, amplitude is different, frequency is different. Mu is different. Yeah, nothing is same there. Okay, done. Then you just need to put it in the formula. So power 1 half mu amplitude square omega square. Omega is 2 pi f v wave. So v wave is how much? I'll write down everything. So mu is how much? I'm using the formula. Power is equal to half mu a square omega square v wave. So rho pi r square, that is your mu. Amplitude is a square. Omega is 2 pi f. V wave is root over tension, which is mg by mu. Mu is again rho into pi r square by power of the second guy, which is half rho. Radius has become double, pi into 2r ka whole square. Amplitude is double, 2a ka whole square. Frequency is also double, 2 pi 2f ka whole square. This will be 2 mg by rho into pi into 2r whole square. Yeah, that's a big thing. We need to simplify this. They'll all cancel out, and yeah, people did get some answer. 1 by 32 root 2, it seems. You can check. Some you got at. Who else got the same thing? Utsa also got the same thing. Yeah, you can. I wrote everything. You could have simplified it further and then you could have done it, but there. Clear what happened there? Your frequency was different, amplitude was different, mu was different, tension was different, so wave speed was different. Everything has changed. This is how they can play around. You should know your formula and you should know what to change there. Clear with this? So today the main two things we did was the wave speed and energy in a progressive wave. These are the two main things. Next class, when we do it on Thursday, will be the very important class. We will be doing something called principle of superposition, reflection of waves, and then we will do a little introduction of stationary waves. Stationary waves is the most important thing in entire waves. So in entire waves, if you see, there are primarily three main concepts. Stationary waves, Doppler effect is removed from the portion, but yeah, that is one. And second thing, the reflection of waves. So next class will be an important one. So we will do more on that. I think another 2 more classes, we should finish a bulk of the chapter. You can start doing waves then, but do finish your ray optics ka pending, whatever you have. So I think with that, we'll wrap up for the day. We did almost 10 questions. So please make sure to go through these things, give it a try. Right? They're not tough, but yeah, mathematically, they're a little more there. So yeah, I'll see you guys on Thursday, same time. So any doubts, anything else, please stay back and ask. I'll be free to give.